So this is using Maple to solve linear programming problems. And homework 3 consisted of these problems. And I'm going to use Maple to solve them. So the first thing to do is to share the screen with a Maple desktop. So this is some Maple work, but what I'm going to do is maybe start with a new worksheet. Make it a little bigger by clicking on the plus sign. And use this to solve our Maple problems. So let's sort of explain what this is. First of all, in Maple, you use the sharp sign to just write a note. So this is using Maple to solve homework 3 problems. So first thing I want to explain is how to define a function in Maple. And a function in either 1 or 2 variables. So if you want a function in 1 variable, let's call it f, you do f colon equals. So colon equals the assignment operator. And if it's going to be a function, you write, depending on what the variables could be anything, x, y, z, x1, z2, let's just make it x. And then I want a right arrow going to the right. And a way to do that is a minus sign followed by the caret, the shift over the period. There's a greater than sign. And let's say this is just x squared. So now this is the function f of x equals x squared. So f of 0 is 0. F of 2 is 4. F of minus 3 is 9, and so on. If we want to graph this function, we can plot f of x. So this is the syntax. Plot parenthesis, then the function. If I just write comma x, that graphs it automatically from minus 10 to 10. If I want to graph it for a different region, maybe from minus 2 to 3, I go x equals the lower limit, minus 2, 2 dots, and then 3. And here we have a graph from minus 2 to 3. If you want to have a function of 2 variables, which is typically what the objective function in the problems in this homework consist of. So you can name the two variables however you like, xy or x1, x2. Let's say I want to define a function of 2 variables, so f colon equals, and then I put in parentheses the 2 variables, which I'm just going to call x1, x2, the minus sign, the greater than sign. Let's say it's 3 times x1 plus 5 times x2. That's my function. So for example, f of, let's see, what is f of 1 comma 0? When x is 1 and x1 is 1 and x2 is 0, this should just be 3. F of 0 comma 1 when x1 is 0 and x2 is 1, this should be 5. F of 1 comma 1, when both variables are equal to 1, this is 3 plus 5. 8. What about when f is 4, x1 is 4, and x2 is, 2. So what will the answer be? 3 times 4, that's 12, plus 5 times 2 is 10, 22. Yeah. So this is the proper syntax for constructing a function of two variables, which is typically what an objective function looks like. Now, we usually have constraints. A constraint is something like, I'll just make one up, 2 times x plus, sorry, let me use x1 and x2. 2 times x1 plus 3 times x2 less than or equal, let me take that from this, less than or equal to 7. So that's a constraint, and we might want to graph it. What does it look like? So you can graph an inequality, you can plot an inequality, but that's a more sophisticated plotting command. And we need to open the plots package. So we say with and in parentheses plots. And now we can use any of these commands. And there's one called inequal. So let's see if we can plot this. So inequal and let's give a range of values for x. Maybe x goes from, I don't know, I'll just make up some numbers, -3 to 8, and x2 goes from, let's say, also -3 to 8. Let's see if this works. Oops, let's see. What is the problem? Oh, I forgot the 1 here. I just wrote x. Perfect. So from -3 to 8, it's this blue region. Now, if you don't like blue, you can change the color. You can say, I don't know, color equals red. Oh, very nice. It's up to you. Now, suppose you only want points in this that satisfy this inequality and that are also non-negative. So here we're graphing now not just one inequality, but we want to include the condition that x1 is greater than or equal to 0 and x2 is greater than or equal to 0. So if I have multiple inequalities, I put them, so x1 greater than or equal to 0, x2 greater than or equal to 0, curly bracket. So let's plot that now. And what we get is just this little piece, right? So this is the feasible region with no condition that the coordinates are non-negative. So you have some negative numbers in here. But if you say x1 greater than or equal to 0, x2 greater than or equal to 0, and this inequality, it's just this small triangle. Suppose we had another inequality. I just change the numbers. I don't know, make this 5x1 plus 2x2 less than or equal to 17. See, what does that look like? With the non-negativity conditions. Let me make it 14 instead. Yeah, there we go. Okay. It's this region. So suppose we want to know what points satisfy both of these inequalities at the same time. So I just say, so here I'm saying, graph all the regions in the first quadrant that satisfy this inequality. I also want to satisfy this inequality. So let me also insert that in here. So we're looking at everything under this line and this line. So we get this region right here. Okay. Now, what typically happens is if you're trying to maximize an objective function or minimize it, that the critical value will occur. It has to occur in one of the, somewhere in this red zone. But it also is normally going to be at a corner of the region, at least if there's a unique solution. So it's easy to find the corners on the X and Y axes. What are the coordinates of this point? Well, the coordinates of that point are the coordinates of the point where these two straight lines intersect. In other words, it's where we can find simultaneous solutions to the equation 2x1 plus 3x2 equals 7 and 5x1 plus 2x2 equals 14. So we have to know how to solve an equation in Maple. And the simplest command is just solve. And then what are we solving for? Well, not an inequality, but we want points on the two lines. So one line is 2x1 plus 3x2 equals 7. The other line is 5x1 plus 2x2 equals 14. And when we're solving more than one equation, we put the equations in curly brackets, comma, and then in curly brackets, the variables we're solving for. So the coordinates of this point are 28 over 11 and 7 over 11. If you want the coordinates as a decimal, you use the command fsolve. F stands for write the answer as a decimal. 28 over 11 is 2.54. 7 over 11 is 0.63 to 10 significant digits. So those are the coordinates of this point. Now, suppose we have an objective function that we want to, let's say, maximize in this red region. So let's call it Z. So that C is the function, not just make it X plus Y. Oops, sorry, not X plus Y. Z colon equals x1 comma x2 goes to x1 plus x2. Now, for any given value of Z, x1 plus x2 is a line with like x1 plus x2. Let's just say, suppose we wanted to plot x1 plus x2 equals, I don't know, 3. Say x1 goes from 0 to 8, and x2 goes from 0 to 8. Oops, sorry, can't do that. If I'm plotting a function in two variables, I have to use the command implicit plot, which is when I open the plotting package, The implicit plot is something that came up. That's what it looks like. If I change this to 2, look like that. If I changed it to 7, looks like that. Well, suppose I put a couple of these together. X1 plus X2 equals 1. So I want to plot X1 plus X2 equals 1. Maybe X1 plus X2 equals 2. X1 plus X2 equals 5. I get these lines. They're all parallel with slope 1, slope minus 1. But there's an easier way in Maple to plot, if you have a function that say of X1 and X2, different values of it in a region, and that is the command contour plot. Let's see. So if I type contour plot, my function z, and let's see. And I'm going from X1, oops. I want it to be X1 goes from 0 to 8. Just want to copy and paste. And how many contours? Maybe 6. Oops. Let's see. X1 plus X2. Let's try that. There we are. So these are contour lines. 6 of them. And this is my feasible region. Let me make it just from 0 to 8 because I'm only looking at the first quadrant. So when we solve a linear programming problem graphically, we draw these contour lines on the feasible region graph and see where is the point that hits the y-axis, the x2 axis, as high as possible. So it would be nice to be able to superimpose these two graphs. So let me just call this feasible region. And maybe I'll just do it from 0 to 4. That's all that's really going to be relevant here. That's my feasible region. And my contour plot, I'll call this objective function. I'll also make this a plot from 0 to 4. There it is. And what I would like to do is put these two graphs together, one on top of the other. So let me try the following command. I'll call it display. And here I gave this plot the name feasible region. And this plot I gave the name objective function. So if I display feasible region, comma, objective function together, I have to spell it correctly. So the red is the feasible region, and these are contour lines. So here's one, and here's one, and here's one. And the question is, what is the line that goes through that point? That is, what is the line parallel to each of these that goes through that point? So you can do it with pencil and paper if you're doing everything with pencil and paper, but it looks to me like that point is the intersection of these two lines. I found the intersection of those two lines right here. X1 equals 28 over 11, X2 equals 7 over 11. So if I evaluate my objective function z at these 2 points, let's see what I get. So z evaluated at 28 over 11, comma, 7 over 11, to move the cursor to the right. That's what I get as a decimal is 3.1818. So let's write about there. And the line parallel to that, going to this point, yeah. So the maximum value of z1 plus z2 going through this point is this. It's just sort of draw a nice, have Maple draw a graph to show that. Let's see. This was my feasible region. And suppose I just do the following. Suppose I'll call this, I don't know, max. And that's going to be what I get when I plot the line z of x1, x2 equal to 35 over 11 as x1 goes from 0 to 4, and x2 goes from 0 to 4. Let me write this. Oh, let's see. Let me write this as x1 plus x2 implicit plot. There it is. So that's max. And now let me display the feasible region and just this one straight line, the max. Perfect. So here, let me try one other thing. I don't know if this works. Color equal blue. Can I change the color? Yeah. So the red is the feasible region. The blue is the line x1 plus x2 equal 35 over 11. You see the blue just touches the feasible region at this corner point. If you look at all the lines parallel to this line, in fact, let me maybe just even put in objective function. So the black are all the lines, this family of parallel lines with slope -1. And the blue is the unique line parallel to these, which intersects the red feasible region and gives you the largest possible value of x1 plus x2. So if this were the mathematical model for a linear programming problem, this is one way to solve it. So I want to use our Maple technology now to solution to problem 3.1-17. So in this problem, the objective function z is 40x1 plus 50x2. Oops. I need to put this sharp sign because this is just a comment. It's not a command in Maple. So in this case, my objective function is x1, x2 goes to 40 times x1 plus 50 times x2. 40x1 plus 50x2. And we have some constraints. Let me just call them constraints. So there's a family of constraints. Let's see. Oops. What happened there? I lost my share. Let me go back to the share. Okay, sorry. So this is problem 3.1-17. The objective function is x1, x2 is 40x1 plus 50x2. And sorry, constraints. Let me use a lowercase. It doesn't matter, but I'm going to put the constraints in square brackets. So what are the constraints? Well, one constraint is that 2 times x1 plus 3 times x2 is greater than or equal to 30. The second constraint is that x1 plus x2 is greater than or equal to 12. The third constraint is that 2 times x1 plus x2 has to be greater than or equal to 20. And we also have non-negativity conditions. x1 greater than or equal to 0, x2 greater than or equal to 0. So 2x1 plus 3x2 greater than or equal to 30, x1 plus x2 greater than or equal to 12, 2x1 plus x2 greater than or equal to 20, x1 and x2 both greater than or equal to 0. So those are the constraints for this problem. Let's see. My feasible region is what I get when I plot my constraints. Let's say x1 goes from, I don't know, you always experiment and then you change it. Let's say 0 to 30, comma, x2 goes from 0 to 30. So it's this region up here. It's a big region. Right? And notice it's above these lines because all of my constraints were greater than or equal to. And the contour lines for my objective function are, let's see, contour plot. And my contour plot is (40x1 plus 50x2 . X1 is from 0 to 30, x2 from 0 to 30. And let's say I have 5 contours. So that's what it looks like. Let's change the color of this. Let's make the color orange. There we are. Looks more like red, but that's orange. And what we want to find is the line parallel, that is the line 40x1 plus 50x2 equals z, that is a line parallel to these, which has the smallest possible value for some point in this orange region. So the point that crosses the x-axis, the x2 axis, as low as possible, but going through. So let's just draw these two together. So let's say display feasible region and objective function together on the same graph. So here's the feasible region, and these are these lines of the objective function. If I click on scaling constraint, now it's drawn to scale. So these lines aren't really, these lines don't have slope 1. So what is the line parallel to these lines, this family of parallel lines, that touches some point in the orange region and hits this axis as low as possible? Right? Well, that's where this line and this line intersect. What is this line and this line? Let's see. When we graphed our constraints, we had 2x1 plus 3x2 greater than or equal to 30. So when 2x1 plus 3x2 equals 30, if x1 is 0, x2 is 10. So this line that hits the x2 axis at 10, that's this line. The line where x1 plus x2 equals 12, that's this line. That doesn't even hit the red region. And with a line where 2x1 plus x2 equals 20, that's this line. So this point is the intersection of these two lines. And let's find the coordinates. Let's solve we have the equation. Let me just copy this and then cut and paste. We want to solve 2 equations and 2 unknowns. So this equation we don't need. It's 2x1 plus 3x2 equals 30. 2x2 plus 2x1 plus x2 equals 20. So those are my two equations separated by a comma in curly brackets. And then in curly brackets, the two variables I'm solving for. And the answer is when x1 is 7.5 and x2 is 5, the objective function has its smallest positive value. Z was my objective function. Z of 15 over 2, comma 5 is 550. So this is the solution to problem 3.1-17. The minimum value of the objective function subject to the constraints occurs at the point 15 over 2, 5, and the minimum value of the objective function is 550. Then we're asked, how does this optimal solution change if the objective function is changed? So here is the old objective function. And we want to change it to z is 40x1 plus 70x2. So this is the solution of, let's see, let me just go back to the top. Here I'm solving 3.117a. And now I'm going to solve 3.117b, which is a different objective function. That's it. But the same constraints. So my objective function graph is going to differ. So I've changed the objective function. And this is now a 70 instead of a 50. And when I plot the feasible region, which hasn't changed, and my new objective function together, I get that. So now these are the parallel lines. And where is which of these lines is going to give you the smallest value of z for a point in this feasible region? So just doing this visually, it looks like right here where you hit the x1 axis, you get the smallest possible point. That is the point, looks like the point x1 equals 15, x2 equals 0. Okay. This is the line two x1 plus 3x2 equals 30. When x2 is 0, x1 is 15. When x1 is 0, x2 is 10. Looks like right at that point. So the minimum value, the solution, will be z evaluated at 15, that's my new z, 15 comma 0, that's 600. So that's the solution to 1b, 3.117b. Part C is, how does the optimal solution change if we change the third constraint? The original constraint is, the third one, is 2x1 plus x2 greater than or equal to 20. We want to change that to greater than or equal to 15. Let me just label what we're doing. This is part C. So those are our new constraints. And our new feasible region is going to be this. Let's change the color to green. So this is the old feasible region. This is the new. You see, they're different. Here you have a corner point here. Now the corner point is up there. So when we change the inequality, we change the feasible region. And there's an ambiguity here, which is let's go back to the original objective function. The problem doesn't say whether we want to change it or not. This was the original objective function. And if we look at the contour plot of this new objective function, or the original objective function, really, it looks like that. And then if we display together, well, let me just copy the command from above, it's easier. So here is the feasible region. This is our objective function. And actually, it's very interesting. If you look at this, our new objective function, a new feasible region, there are actually two corners. You have to look at it carefully. Here and here, in addition to the 3 on the axis. So there's 4 on the 2 on the axis, this and this, but 1 and 2. So it's not so clear without working it out carefully where you get the minimum value. Let me put in, just double the number of contours. So you have to find the coordinates of these two corner points and see. I mean, it looks like this is where you get your minimum value for the objective function. but it's easy enough to calculate them. So let's do that. So we need to solve two different inequalities. So what were our constraints in this problem? 2x1 plus 3x2 equals 30. And 2x1 plus x2 that's it. So this line, this line is the line 2x1 plus 3x2 equal 30. And this line is 2x1 plus x2 equals 15. So that's the solution of that. And our second pair of equations, we have this line, which is this line is 2x1 plus 2x2 equals 15. And this line is x1 plus x2 equals 12. I just need to write these down so I don't remember. So 2x1 plus 3x2 equals 30, x1 plus x2 equals 12, and 2x1 plus x2 equals 15. So this corner point is on this line, 2x1 plus 3x2 equals 30. And on this line, which is x1 plus x2 equals 12. Sorry, it was changed to 15 equals 15. And this point is on the line 2x1 plus x2 actually, it's easier to look here. So this point is on the line 2x1 plus 3x2 equals 30, and x1 plus x2 equals 12. Right, that's what I got. And this point is on the line x1 plus x2 equals 12. And this line, which is 2x1 plus x2 equals 15. 2x1 plus x2 equals 15. this line is still x1 plus x2 equals 12. So one corner point has these coordinates, 3/2 and 9. The other corner point has coordinates. What happened to them? So 2x1 plus x2 equals 15. x1 plus x2 equals 12. The points 3 and 9. So that can't be right. Cos x2 equal 9 doesn't go through though for those points. Let me just go back and see. What are my equations? 2x1 plus 3x2 equals 30. x1 plus x2 equals 12. And 2x1 plus x2 equals 15. So those are the constraints. And that is the feasible region. This is the contour plot of the objective function. This is the contour plot superimposed on the graph of the feasible region. And these two corner points, what are their coordinates? Let's see, this line is x1 plus x2 equals 12. And this line, so we have x1 plus x2, oh, this is still a 2x1, that's the problem, right problem. Okay, so one point is 6,2, the other point is 3,9. What is the value of the objective function at the point 6,6? It's 540. What is the value of the objective function at the point 3,9? It's 570. So the minimum value is of those two is 540. So minimum value of the objective function is 540 at the point 6,6. That's the solution. Very good. Wow, took a while, but this is using Maple to solve a linear programming problem. There are very few commands, but the syntax is very important. Anything that's off in the syntax, Maple will give you an error. So it takes a while to get the Maple program to run properly, but it certainly ran here. So, and I will copy this and post the Maple worksheet on Blackboard, and the lecture will be posted on YouTube. So that's where we are. And I guess that will be the end of this little lecture.